This is Lab 2, Motion of a Falling Object. This is a table of contents and the introduction. The purpose of this lab is to observe the motion of an object that is dropped from rest and falls somewhat slowly and straight down. Then I'm going to compare these observations to a computational model that has and then also doesn't include drag. The assumptions that we're making is that there's going to be negligible motion in axes other than the y-axis because we're going to be dropping it down, so that's the y-axis, and then considering that the dropped object is a point mass. And some key concepts that we want to include are Newton's second law, which is the net force on an object is equal to the change in momentum over the change in time, which is represented by those formulas right there. And then that formula can be translated into the velocity update formula, and we'll be also using the position update formulas, one with the non-constant force and another that has a constant force. And this is what the results will end up looking like, with an object having a downward net force. So as time goes on, the displacement between the object will increase. And on to the experiment. First, going over the free body diagram. So the paper ball that I will be dropping is going to be represented by this black circle, and it has two forces acting on it, a downward force of gravity and an upward force of drag. So the F net will be the force of drag minus the force of gravity, and then when you plug in its equations, it'll be bv squared minus mg. And note that the force of drag will increase as time moves on because it relies on velocity, and velocity will increase as time goes on. And let's also remember that the system is going to be the paper ball that I am dropping, and the surroundings will be everything else. This is the tracker video analysis. Take note that the axis was flipped to account for the fact this video was accidentally taken sideways. So the negative y-axis will be acting in the right direction, and that was me dropping the paper ball. Next is the data analysis. This is the data table taken directly from Tracker. And then I turned it into a graph, which looks like this, kind of like a downwards parabola. Next is the computational model, where I only took gravity into account. So these are the initial conditions, and note that the force is just the force of gravity, which is in the negative direction, only in the y direction. And then I made the initial conditions right here, as well as put in the net force inside the iteration. And I also use the velocity update formula and the position update formula that accounts for a constant net force, since the force of gravity does not change throughout this entire observation. And the full code can be seen at this link. And now this is the computational model with drag. Notice how the net force changes here as we include drag, which is bv squared. So the net force in the y direction is bv squared minus mg. The initial conditions are the same except for the b value at the bottom here, which is different because now we have drag. And for F net, notice how I changed the formula to account for drag, and then I also use a position update formula that has a non-constant net force, since the force of drag is a non-constant force. This is the comparison graph with the two computations and the physical observation. And now we'll be moving on to the discussion. So first we realized that the graph with drag is more accurate to the physical observation than the graph that did not show drag. This was an expected outcome, as the force of drag does act on the paper in real life when it is dropped. The second thing we learned is that the computational model with drag resulted in less displacement than the model without drag. So the additional drag force opposes gravity, which reduces your net force, acceleration, and velocity, resulting in less displacement covered over time, so we observed less displacement. And some potential errors can be not correctly selecting the center of mass when doing the tracker analysis, impacting the position recorded and velocity calculated, and also incorrectly approximating the b value, or the coefficient of drag, will impact your net force calculated and the velocity calculated. And then we can have errors when rounding the small numbers, reducing the accuracy, and also not taking motion along other axes into account can impact the accurate position. And now on to the further questions. The first one being, which models, if any, predict a terminal velocity? And that will be the computational model that includes drag, which is the graph on the right. This is because the drag force opposes the force of gravity, which balances out, resulting in a constant velocity over time, which is the terminal velocity, as seen by like the flat line towards the end of the right graph. And the one on the left is the computational model with just gravity, which you can see no terminal velocity shown because there's nothing opposing. And now onto the what if question. If the object was initially thrown downward, it would reach the same velocity just at an earlier time as shown by the computational model on the right, which has the downward velocity. And for the conclusion, when an object is dropped, it interacts with two forces, force of gravity and the force of drag. The force of drag changes over time as it varies with velocity, and a computational model that includes drag is more accurate than one that only includes gravity. Thank you.